So thank you so much for coming today. I'm Dr. Matt Shultz, for anyone who just joined. This is my final talk as the Annie Jump Cannon Fellow at the University of Delaware. So I thought how appropriate to talk about the end of the world, the end of the universe, in fact. This is something that I've taken kind of a morbid interest in for some time, so I'm kind of looking forward to talking about it. So the universe is, as we usually think about it, quite old. It's about 13.4 billion years old is a modern best estimate. So it started with the Big Bang. If you organize the universe's, if you condense the timeline into 1 year, it helps to visualize what's already happened. So the Big Bang started on January 1st. The first stars started forming around February. The first galaxies started to condense in March. Then you had several months of just ongoing star formation and chemical enrichment of the primordial hydrogen-helium mixture by nuclear processing inside stars that then blow up in supernova and return that material to the interstellar medium. And around September, the sun and its planets start to form. Earth takes its final form around the beginning of October. Life actually originates sort of shortly after that in November, but it's mid-December before we get any multicellular life. And humans come along, of course, very late in the day. You could condense our entire history, our entire recorded history, into the last 23 seconds of the cosmic calendar. And in this case, I'm taking the reference point as being Göbekli Tepe, which is dated to 9000 BC, roughly. This is the earliest stone structure that we found. And while we cannot translate the markings on the stele yet, they do clearly encode some form of information. So I personally consider this to be the beginning of recorded history, rather than the commonly given date of 5,000 years ago. As for an individual human lifespan, that would come down to about 0.2 seconds, roughly equivalent to 1 blink. So your life is a cosmic eye blink. And you know, when you look at things on that vast scale, 13.5 billion years, the universe really just seems incomprehensibly old to us. It's really hard to wrap our minds around just how vast the deep time of the past is. But this is actually a profound misunderstanding of the nature of the universe, because the truth is, it is actually incomprehensibly young. I should mention that these last two images and a few more that I'll use in the talk, I got from the Melody Sheep YouTube channel, who do, I think, some of the finest scientific visualizations, like astronomy visualizations specifically, currently, that have ever been done, in my opinion. They're really just gorgeous, and you should check them out if you have the time. Melody Sheep. So we know the universe is 13.5 billion years old because when we look at galaxies that are far away from the Earth, their light is shifted to the red. Light is a wave, and when a wave, when the object emitting a wave is moving towards you, the wavelength gets stretched out. So in light, that means it goes to the red end of the spectrum, and if something is moving towards you, that the wave gets condensed, and in terms of light, that means it goes to the blue end of the spectrum. So from that, we have a pretty good idea that the universe is actually expanding, because all of the galaxies we look at are redshifted. And furthermore, the dimmer a galaxy is, the more redshifted it is. So that tells us that the universe is, well, expanding. It also enables us to use the redshift as an indicator of the distance to the galaxy, specifically the distance the galaxy was from us when the light was emitted. Since the universe is expanding, and since the speed of light is finite, that means that the actual galaxy itself that emitted that light at the time when we see it has already moved much further away. So what you're seeing here is the result of a very large redshift survey where they can actually infer the three-dimensional structure of the universe just from looking at where a galaxy is in the sky and how redshifted it is. Now, if we take that and we just run it back in time, we, assuming sort of a certain rate of expansion, we can infer how old the universe is. This is how we know that it's 13.5 billion years old. And as you can see from here, there's a few different models for how the universe might be expanding or contracting. And we'll talk about those a bit. So if the universe has too much stuff in it, too much mass, then at a certain point, as it's expanding, all of the gravity from all of that matter will start to overpower that initial impulse in the Big Bang that made everything start expanding in the first place. And the universe will start contracting again. And ultimately, it will come around to back to a single point, a singularity, in an event that we often refer to as the Big Crunch. And as the diagram on the left sort of indicates, this kind of Big Crunch scenario could indicate a cyclical nature to the development of the universe, where the Big Crunch then rebounds into another Big Bang, which then collapses into another big crunch. And this process could go on perhaps indefinitely. But we actually don't think that's what's going to happen anymore. So we need to know how much stuff is in the universe. And of course, we can look at a galaxy and sort of guess how many stars are in it. And we know roughly how massive a star is, and we can guess roughly how much mass is in the stars. And then if we look at radio wavelengths, we can guess how much matter there is in gas and add that together. But another way to get mass is to look at how material actually moves. So if we use that same Doppler effect that I mentioned before for the expansion of the universe, for the cosmological redshift of galaxies, we can actually measure how a galaxy is rotating. And any given spiral type galaxy that we look at will be blue shifted on one part and red shifted on another. It tells us it's, rotating, as you would expect just by looking at the shape of it. And the interesting thing is that when in every single spiral galaxy that we've looked at, what we call the rotation curve, that's just the sort of velocity of the material as a function of the distance from the center of the galaxy, is much higher than you would expect from Newton's laws. And the easiest way to reconcile that with known physics is to assume that the galaxy is surrounded by a large halo of invisible material we call dark matter. So this is the main evidence for dark matter. It's not the only evidence for dark matter, but it is the most often cited and probably the most convincing. And the amount of dark matter actually ends up being a lot more than the amount of regular matter. So that's kind of an important thing to know in terms of, okay, well, how are we going to have a big crunch scenario, or is the universe going to keep expanding? Now, it's also really useful to know exactly how far away things are. So we can kind of guess based on the redshift distance, but that doesn't really tell us exactly how far away the galaxy is. It just tells us how fast the galaxy is moving away from us. And then we sort of guess based on how bright the galaxy is to get how far away it is. But if you can use something that has exactly the same brightness at any given distance, a phenomenon that has exactly the same brightness intrinsically every time you see it, then if you just look at how bright it appears to be, that tells you how far away it is. We call those standard candles. And one of the most useful ones on the cosmological scale is a kind of supernova, which is produced by a white dwarf star. So what's a white dwarf? White dwarf is the dead core of a star. So the star has used up all of its hydrogen, and it has blown off its outer atmosphere. Fusion has stopped in the core of the star, and what's left over is just this kind of glowing coal, essentially. You might have heard of quite a bit about white dwarfs, because I imagine Judy has talked about them on occasion. So the important thing about a white dwarf is it is held up against its own gravity by electron degeneracy pressure. You can just think about that as the star is packed so tightly together that the electrons are kind of bumping into each other and not letting it contract anymore. But that only works up to a mass of about 1.4 times the mass of the sun. So if something happens to increase the mass of that white dwarf, for instance, if it's really close to another star, it's in a binary system, that star is dumping material onto the white dwarf, or if you have two white dwarf stars orbiting around each other and they get close enough that they actually merge, then you now have an object which is higher than 1.4 solar masses, and it goes boom. And the luminosity, the intrinsic brightness of that explosion is more or less the same. So we can use these white dwarf supernova in order to, as a standard candle. And all we have to do is just look in the sky, watch for these events, figure out what galaxy it came in, and that tells us how far away that galaxy is. We can use that as an independent check. And a lot of effort has gone into this over the years, and about 10 or 15 years ago, there's a remarkable result due to some large surveys that found that, in fact, the universe seems to be accelerating. So it isn't just that the universe is expanding, it's that something is causing the expansion of the universe to actually speed up over time. We have no idea what that stuff is, but we call it dark energy. We can't really see it, we can just see its effects. And it seems to completely dominate the mass energy budget of the universe. 68% of the universe's mass energy is in dark energy. Only 5% is in visible matter. Now, those of you who joined a little early would have heard Stan and me talking about this. There's one idea with dark matter, sort of depending on what it is that its influence might actually increase over time. And if that's the case, then at a certain point, according to at least one model, in about 22 billion years from now, dark energy will become so influential that the rate of expansion of space will basically rip individual atoms apart. This is known as the Big Rip. So obviously, if this happens, the universe is basically done in 22 billion years. If the Big Crunch happens, which we don't think it will anymore, the universe is done in about 10 billion years. But in between those two extremes, you have scenarios where the universe just keeps on expanding at more or less the same rate, or kind of maybe only gently accelerating, more or less indefinitely. And my understanding, at least, is that we're actually pretty close to critical, where we should just sort of coast along eventually. So it's these two middle scenarios that we'll really be talking about for the rest of this talk, since they're the ones that provide sufficient time for the really interesting stuff to happen. The final thing that we need to look at as background for the story that we're going to tell is how stars evolve and how this relates to galactic ecology. So stars are born with varying masses. They can be either much less massive than the sun, down to about 10% the mass of the sun, or they can be significantly more massive than the sun, up to 50 or 60 times the sun's mass. In extreme cases, even more than that. Now, the more massive a star is, the more pressure there is in the middle of the star. The higher the pressure, the higher the temperature, the star burns stuff faster. So a more massive star is burning up its fuel much, much faster than a less massive star. The result of this is that even though the most massive stars are sort of 50 to 100 solar masses, they actually burn up all of their fuel in just a few million years. A star like the sun uses up its fuel in about 10 billion years. The least massive stars, M dwarfs, red dwarfs, can last for about 10 trillion years. And they're by far the most common stars in the galaxy. Now, when a star has used up its fuel, it starts to go through a fairly complicated evolution at what we call the end of the main sequence. So a star like the sun will become a red giant and then contract again and then become a red giant again. I'm simplifying. A more massive star will blow up into a blue supergiant and then sometimes become a red supergiant. And this is related to the core of the star starting to burn helium in a shell around the dead hydrogen core. And maybe if it's more massive, it goes up to higher elements. Then when that process is done, you have some kind of remnant left over. So for stars like the sun, or I think up to about 8 times more massive than the sun, that remnant is going to be a white dwarf star like we already described. For stars more massive than that, you get a neutron star. You can think of a neutron star kind of similar to a white dwarf star. It's also a degenerate object, only it's neutron degeneracy pressure that's holding it up, and they're much, much, much more compact. A neutron star is about the size of your average city, but has a mass comparable to that of the sun. More massive still, and the remnant will collapse into a black hole. And for the most massive stars, we think they actually just blow up in a supernova and nothing is left behind. Now, not all of the material is left behind in the neutron star, black hole, or white dwarf. A lot of it is actually returned to the interstellar medium, to the clouds of gas and in between the stars. And this material that's returned is going to contain some of the heavy elements that were formed by fusion in the core in the star over the course of its life. And it's available to form the next generation of stars. But with each generation of stars, a little bit more material gets locked up in the degenerate objects or in the black holes. And that means that eventually you reach a point where all of the material that's available to form new stars is now going to be locked up in these degenerate objects. So that's all the background that we need. Now let's look at what is actually going to happen next after our time in the universe. So first, I hate showing math in talks, especially in talks for the public. This is all the math that you're going to get. So just for convenience, because the timescales we're going to be talking about are just insanely long, we will be using the cosmic decade, which I'm going to call tau, the Greek letter tau, because astronomers love to use Greek variables, which is simply the log of the time in years, the base 10 logarithm. So each power of 10 is 1 in log, right? So 10 years would be 0, and 100 years would be 2, and we're about 10 billion years, roughly, order of magnitude after the beginning of the Big Bang. So we're at log of 10. So the next thing, or the first thing, will be humanity sending its first probe to another star, if this actually happens, which I hope it does. So there's a plan to send a fleet of very small spacecraft boosted with light sails, boosted up to about 10% of the speed of light, or 5% of the speed of light, something like that, with lasers, and do a flyby of the planets in the Proxima Centauri system. That's the red dwarf star, which is the closest star to us, about 4 light years away. In about 2200 AD, humans will become a type 1 civilization. So this is from the Kardashev scale. The Kardashev scale describes, classifies civilizations according to how much energy they use. A type 1 civilization uses all of the energy in one planet, has total control of that. And at the rate that we're increasing our energy use, it's, if you just extrapolate that out, we should reach that by about 2200 AD at the latest. Just a few thousand years after that, we'll reach type 2. A type 2 civilization is a civilization that controls all of the energy output of one star. This involves building something called a Dyson swarm or Dyson shell around the star in order to collect all of its solar energy. Notice that tau up in the corner hasn't changed from before. In about 100,000 years, Betelgeuse will go supernova. So Betelgeuse is the red supergiant star, descendant of a main sequence massive star, which is the closest red supergiant to Earth. When it explodes, expected sometime in the next 100,000 years, it could happen tomorrow for all we know. And some of you probably recall there was some speculation that it might happen last year when the star suddenly dimmed. But it should happen within 100,000 years. And when it does, it will be about as bright roughly as the full moon for some period of weeks. In about 10 million years, humans, and I put that in quotation marks because at this point, are we still human? Are we still talking about humans or distant descendants of humans? I don't know. Probably not actual humans as we would recognize them, but finish colonizing the Milky Way galaxy and become what's referred to as a type 3 civilization. That's a civilization that controls all of the energy output of one galaxy. And this timescale is assuming that our maximum speed of travel between stars is about 1% of the speed of light, really just crawling along by the standards of interstellar travel. If it's 10 times slower than that, it will take 10 times longer. And that doesn't make much of a difference, in fact, to the placement of this event in the timeline. And finally, you'll note, tau is finally changed by 1 digit. In 250 million years, continental drift will have carried all of the continents of the Earth into Pangaea Ultima, the final supercontinent. Those of you who enjoy looking at total solar eclipses will be very disappointed in about 600 million years when the last total solar eclipse happens. And this is because the moon is gradually moving away from the Earth. So there's tidal friction between the moon and the Earth. And we all know the tides in the oceans. That's caused by the gravity of the moon. And the mutual tidal influence of the Earth and the moon is gradually slowing down the rotation of the Earth and causing the moon's orbit at the same time to gradually increase. Basically, the moon is stealing angular momentum from the Earth's rotation. And because it's moving gradually away, at a certain point, the moon will no longer be sort of exactly the size of the sun on the sky. And the result of that is you will no longer have total solar eclipses. In about 1 billion years' time, tectonic activity is projected to stop on the Earth. So we hear a lot about how important it is to reduce CO2 levels these days in order to forestall global warming. But of course, carbon dioxide is extremely important to the ecology of the planet because that's what plants breathe. And the carbon cycle is, well, a very important part of that is the tectonic activity that sort of replenishes carbon from the inside of the Earth. When tectonic activity stops, that carbon will gradually get sequestered in rocks and it won't get replenished anymore. And the result of that is there won't be anything for plants to breathe, which means photosynthesis will end, which means the oxygen will disappear from the atmosphere and the Earth's atmosphere will become unbreathable. The surface of the Earth will become basically unable to support complex life, or possibly any life. Things get even worse in about 2.7 billion years when the Earth's oceans evaporate. So the sun, as it evolves across the main sequence, it hasn't become a red giant yet, but it is getting gradually brighter. Its luminosity is gradually increasing. And that means that at a certain point, the temperature on the Earth will go high enough that liquid water can no longer be sustained on the surface, and we lose our oceans, become a desert planet. But we already lost our atmosphere 1 billion years before this. The good news is that Mars, which is currently at the outer frigid end, technically, of the habitable zone, that's the zone around a star where liquid water can exist given how bright and hot the star is. Mars will move from the outer cold edge of the habitable zone to the nice, comfy middle of the habitable zone. And if we've successfully colonized the entire galaxy and set up a type 2 civilization, I'm sure that we will be easily able to terraform Mars and make it a nice habitable world, which should stay quite comfortable for about 1 billion years. Now, in about 4 billion years from now, the sun will become a red giant star, getting very close to the end of its life as a star. Interestingly, so Mars, of course, at this point will no longer be in the habitable zone, but Jupiter will be. Now, of course, we can't live on Jupiter. It's a big gas giant, toxic atmosphere, strong gravity. It would be horrible. But Jupiter has moons, which have a lot of water. Currently frozen. Europa is the most famous example of this. It's believed to be covered by an ocean 50 kilometers thick underneath a very dense ice sheet. If Jupiter is in the habitable zone, its moons will be too. So for a period of, I think, a couple 100 million years, Jupiter will be in the habitable zone, and possibly one or more of its moons might become a nice place to live. Around the same time, Andromeda, which is the closest large galaxy, closest spiral galaxy to the Milky Way galaxy, will collide with our own galaxy. And on the left here, you can see some ideas of what our night sky might look like throughout this period. So you can see Andromeda getting gradually closer to the Milky Way. And then when the galaxies collide, you have these very chaotic tidal streams that are ripped out of both of the galaxies. You can see all of these red and blue spots here. This is because the gas clouds in the galaxies colliding with one another cause a sudden burst of star formation. So you just have what is effectively a massive baby boom between the two galaxies. But after a period of time, all of that material, actually, all of that free gas gets used up really, really quickly in this collision. And then all of the blue stars, the massive stars that live very short lives, they're all dead. They go supernova, they're gone. And all that's left are the less massive stars, stars like the sun and stars of lower mass, which are kind of redder, yellow-red stars. And that's why the night sky is now going to be sort of a little bit less exciting. You'll also notice that it becomes kind of just a big blob. And that's because once all of those tidal streams settle down, that delicate spiral structure that Andromeda and the Milky Way both have is completely destroyed, and you end up with what's called an elliptical galaxy. And that's basically the form that what we have to refer to now as the Milk-Dromeda galaxy will have for the rest of time. In about 5 billion years, the sun exits the red giant phase and finally becomes a white dwarf star. So the white dwarf star in this image would be this little dot right here in the middle, and this really gorgeous, really spooky looking planetary nebula around it, or all the outer atmosphere of the star that gets ejected during the final phases of the star's life. So white dwarfs just kind of cool gradually over time. They start out, they just came out of the inside of a star. They started extremely hot, like 50,000 degrees, but over time they cool, as any coal will cool when you take it out of the fire. And we actually know that they crystallize. And this is a pretty long process. In about 10 billion years time, the white dwarf sun will have crystallized. So, of course, the Andromeda galaxy is not the only galaxy close to the sun. There are actually quite a large number of much smaller galaxies in the area, a whole swarm of them around our own galaxy, and a whole swarm of them around Andromeda, and a few others here and there. We refer to all of these galaxies as the local group. After the Milk-Dromeda galaxy is coalesced, that big elliptical galaxy, all of those other galaxies, which are also gravitationally bound to the system, will, over time, gradually be absorbed by the Milk-Andromeda galaxy that will basically eat them. And that process will be complete in, well, I'm just gonna start using tau now, at tau of 11.21. So at that point, from there on, the local group is basically just one big elliptical galaxy. Now there's a larger region, which you refer to as the local supercluster, much, much, much larger than the local group. And around the same time that the Milk-Andromeda galaxy has finished eating all of the little galaxies around it, the universe, of course, is continuing to expand. And at a certain point, the expansion of the universe gets to, so far that more distant parts of the universe actually get carried beyond the observable horizon. So this means that their expansion is basically faster than the speed of light, and light emitted from those galaxies can no longer reach us. So we just fall out of causal contact with the rest of the universe. At tau of 14, the last star is born. So now all of the gas has been used up, and that final star starts its life at the beginning of the main sequence. At tau of 14.01, the last red dwarf star dies. So red dwarf stars, remember, they can have lifetimes of up to 10 trillion years. So from tau of 14 to 14.01, we have moved 10 trillion years into the future. So as the last star dies, the sky basically goes dark. This is the beginning of the degenerate era. I should mention that the sky to human eyes would be quite dark before that. So earlier in the talk, I mentioned Proxima Centauri, closest star to the Earth. What's very interesting is that Proxima Centauri is much too dim to be seen with the unaided human eye. So when the majority of stars in the galaxy are red dwarf stars, which they will be after probably about 1 trillion years after the, certainly within 1 trillion years of the last star being born, the human eye would not be able to see really anything in the galaxy. For those music lovers here, the degenerate era is the title of a atmospheric black metal album by a group I really adore called Nazartham. And I would be lying if I said I was not listening to this album the whole time I was preparing this talk. So at tau of 15, where I said white dwarfs, they just cool over time. All of the light they radiate is just from them cooling down. Well, eventually they cool down so much that they basically reach the cosmic microwave background temperature, which means that they would become completely invisible. You would not be able to distinguish them against the sort of glow of space itself, left over from the Big Bang. And at this point, we refer to them as black dwarf stars. Now, there's two things that will affect planetary systems. You imagine some of these black dwarfs would still have planets that would have survived the red giant phase, orbiting around them, possibly for a very long time. But over these very long spans of time, it would sometimes happen that another star would come just close enough to that planetary system for its gravity to disturb the orbit of that planet and kick it out of the orbit of its home star and possibly eject it from the galaxy. In other cases, there's gravitational radiation. This causes the orbits of white dwarf stars, for instance, or neutron stars to decay over time. And it's not a terribly important thing in the timescales of the universe that we've seen so far in our own experience when it comes to planetary systems. But over these very long timescales, that gravitational radiation can actually, very, very weak effect when we're just talking about a planet, but it can be enough over this kind of timescale that the orbit actually just decays. So, and it turns out that the timescales for stellar flybys, destroying orbits, and orbital decay causing planets to fall into their white dwarf host stars are kind of similar. So around tau of 15, the last planetary system has been destroyed one way or another. And of course, these close flybys that can perturb the orbits of stars can also eject stars from the galaxy. So that starts happening around tau of 19. The galaxy just starts losing stars. Here I'm actually showing a hypervelocity star that was ejected by a supernova from our own galaxy. Obviously, keep in mind when looking at this image that at this point the galaxy would be invisible. It's nothing but black dwarfs, neutron stars, and black holes. Now, by tau of 30, any star that hasn't been ejected from the galaxy has been accreted onto the supermassive black hole that would have originally descended from the supermassive black hole currently at the center of the Milky Way galaxy, which would have merged with the supermassive black hole at the center of the Andromeda galaxy. The final sort of terminal mass of this object is estimated to be about 10 billion solar masses. Our Milky Way's supermassive black hole is about 6 million right now, so it will grow quite dramatically over this time span. And that'll be about 10% of the total material in the galaxy will ultimately end up inside this gargantuan supermassive black hole. By tau of 37, something very interesting starts to happen according to certain interpretations of certain particle physics theories. And there are several of them that I looked at briefly. It turns out that some of these have been ruled out. They all make different predictions for the time scale when you expect this to happen. But basically, there's a chance that, depending on which theory is correct, that protons could actually decay. Now, protons, one of the three fundamental particles, not quite fundamental, of course, but not quarks after all. But they're the basic building block of atoms, and they're very stable. No proton has decayed, as far as we know, in the history of the universe to date. But by 10 to the 37 years from now, proton decay, if it's going to happen, that's probably about when it will start to happen. So this image on the left, I got this from a CERN webpage. This is like an artist's rendition of like what the inside of a proton might kind of look like, where we think of them in these hard little spheres, but they're actually composed of three different quarks, and then all of these sort of like gluons and sort of fields inside of them. They're actually very complicated environments. And when they decay, if they decay, you'll basically have just gamma rays and positrons be ejected out of them and no more matter. So this actually means that the white dwarf stars start to give off light again, because you have this proton decay, and each time a proton decays, a tiny bit of light is left off. Now, this is a very slow process. So the sort of peak luminosity of a white dwarf star, I should say a black dwarf star, at this point is around 400 watts. So just 4 light bulbs, basically, for each surviving star in the universe. Now, through a complicated series of particle physics cascades that I won't get into, because I am not a particle physicist, it turns out that proton decay will also start converting the neutron stars into white dwarf stars. So eventually, you just have the white dwarf stars, or I should say black dwarf stars. Proton decay, of course, will also affect any planets. So the planets that haven't fallen into their host stars are just kind of these free-floating orphan worlds, but they'll also start to decay. It won't look as exciting as this, of course. By tau of 49, so that is 10 to the 49 years as compared to the process starts in 10 to the 37 years. The white dwarf stars will have lost about 90% of their mass. So each time a proton decays, of course, the white dwarf gets a little bit lighter. At a certain point, it's lost so much mass that its self-gravity isn't actually enough to hold it together anymore. And it isn't actually dense enough to block light. So it just becomes this kind of translucent gas cloud that will just kind of dissipate off into space. And the remaining protons just gradually decay. And of course, the neutron stars will have turned into white dwarf stars and go through this same evolution. So at this point, there's nothing left but black holes. This is what we call the black hole era. Every once in a while, if you have two black holes that are in a binary system, gravitational radiation can cause their orbits to decay, and they'll merge, just like the ones that we see with gravitational wave detectors here on Earth every once in a while. And these will be some of the only events that actually happen, these sort of invisible gravitational waves from merger events propagating through the blackness every once in a while. But by tau of 65, something interesting starts to happen. So space is not actually empty space. There are these things called virtual particles. They're a kind of unexpected consequence of quantum uncertainty, where two particles, for instance, an electron and a positron, an anti-electron, will instantly pop into existence, and then they'll instantly annihilate. The net amount of energy generated is zero. The net amount of mass is zero. And it happens very, very quickly. But we actually have experimental evidence that these virtual particles are constantly popping in and out of existence all over the place. For our daily life, that doesn't make much of a difference. But for around a black hole, Stephen Hawking predicted, and this has been experimentally verified with kind of laboratory analogs of black holes, that a virtual particle pair that comes into existence exactly at the event horizon of the black holes. The event horizon is the point where the escape speed is the speed of light, basically. Anything which is closer than the event horizon is never able to escape from the black hole. Anything which is past the event horizon in principle can, if it can go fast enough. So a virtual particle pair that comes into existence right at that event horizon, one of the pair goes down into the black hole and the other pair escapes. And that actually has the effect of reducing the mass of the black hole over time. So they start to evaporate. And the rate at which this happens is a strong function of the mass of the black hole. The larger the black hole, the larger its event horizon, the slower the rate at which it emits Hawking radiation. A very, very small black hole emits their Hawking radiation so rapidly that it actually sort of explodes in a burst of high energy radiation. And of course, every black hole eventually reaches that. So the first ones to reach that will be the stellar mass black holes. And by tau 65, they'll be evaporating. So every once in a while, one of these stellar mass black holes will actually go, and you'll get this brief burst of gamma rays. Tau of 92, the last supermassive black hole evaporates. And now we enter the dark era. So the universe contains nothing now but photons, and it's still expanding. So as the universe expands, those terminal photons, the last photons emitted in the universe will have been from the evaporation, the Hawking radiation evaporation of the last supermassive black hole. And they'll start at very high energy, but as the universe continues to expand, they'll get redshifted to lower and lower energies. And that's sort of it. There'll be sort of maybe some strange quantum things happening that might turn out to be important. I wasn't able to find much very specific of what happens in the dark era. It's kind of, the end. It's the Fimbulwinter of the universe. And that's the end. Or is it? See, the universe is a really weird place. It's just vast in space and time. And we're used to thinking of it, like I said, at 13.4 billion years old, and, and being like, wow, it's so huge, it's so old, I can't wrap my head around it. But as we just saw, it's going to be so much older than that, and so much more is going to happen. And, this first cosmic year is a fraction of a second compared to the history that is going to unfold, or that we expect to unfold, if the big rip or the big crunch doesn't destroy things first. But of all the really amazing things in the universe, to me, the fact that the universe contains mind is us, right? At least us, maybe hopefully other minds as well, is just incredible. And we often think that we're just this kind of accidental, you know, assemblage of thinking meat that just happened to crawl out of the slime here on one little unimportant dirt ball in an ordinary galaxy, and kind of an emergent epiphenomenon that is of no particular consequence to the universe. Mind is a really weird thing, though. If you think about it, so this talk that I just gave to you, like, you now have in your head kind of a rough sketch outline of the history of the universe so far and a projection of what's going to happen over an extraordinarily like deep cosmic future. And you're able to hold that all in your minds. Isn't that kind of amazing? Isn't it amazing that the universe actually contains the ability to model itself inside of itself? Because if you think about it, we're not separate from the universe, right? We are parts of the universe as well. So this is cosmologist John Wheeler. He started as a physicist, actually got into cosmology later on. Really, really brilliant guy. He did a lot of very important things. And he made this diagram at one point to kind of illustrate like his questions about, what is the role of mind in the universe? So, you've got the U representing universe, right? And you've got this sort of singularity at the beginning. That's kind of like the Big Bang. And then, the universe expands, right? And you have the little arrows here indicating the arrow of time. And then you get up to kind of where we are, and you have observers, intelligent entities that can kind of look around and see the universe and think about the universe, who are actually able to look at, the entire history of the universe. And, he got into some quantum stuff that sounds a little bit like mysticism. But, he's fairly able to, he was someone who knew what he was talking about. And his point was that, is this accidental, or is there a really fundamental role that mind is playing here that we haven't really thought about? So, going back to the beginning of our timeline, the very first thing almost, which seems incredibly far in the future to us, but on a cosmic scale is like, the next moment, is us colonizing the entire galaxy. So, what, and beyond that, there's no reason that life would stop expanding and, building and interacting with the universe on an even larger scale. So could mind actually be play a key role in the future evolution of the universe? And to me, and beyond all of the uncertainties about particle physics or the nature of dark energy, the fact that we don't really know the role that mind plays in all of this, I think could turn out to be decisive. And that is the end of the talk. Thank you so much for listening, and I'm absolutely happy to take any questions.